In this problem, we have an insulating disk of radius capital R and uniform surface charge density sigma. The disk is rotating about an axis perpendicular to its plane with angular speed omega. We'd like to find the magnitude of the magnetic field at point P, which is at a distance d from the center of the disk. To solve this problem, we're going to treat the disk as the combination of infinitely many concentric rings and integrate over those rings to find the magnitude of the magnetic field due to the entire disk. Here's one such ring of radius lowercase r. Now remember, capital R is the radius of the entire disk, but lowercase r is the radius of a single ring, which is a variable depending, each ring has a different radius, lowercase r. Now let's remember the magnetic field due to a single such ring, B ring, is equal to mu0 times capital I, this is the electric current in the ring, times r squared divided by 2 times r squared plus x squared to the power 3/2. Now this is a general formula. Capital I is the current in the ring, capital R is the radius of the ring, and x is the distance from the center of the ring to the point of interest. So these variables do not match this problem's variables because it's a general formula, but in the problem, when we solve the problem, we're going to use the variables as given in the problem. Now the total magnetic field due to the disk will be the integral of the magnetic field due to each ring element. So each ring element will have a magnetic field dB. We are going to integrate over dB. Let's start by substituting the ring formula for dB. So we have mu0. Instead of capital I, I'm going to put di, lowercase I. Why am I doing this? Because each ring has a different current I, so that's why I call it di for now. I'm going to formulate it later on. Now again, each ring has a radius lowercase r, so I'm going to put lowercase r squared here, divided by 2 times, again, lowercase r squared, plus d squared, which is the distance given in this problem, to the power 3/2. Let's come up with an expression for di. This is basically the current in a given ring, right? And if you think about it, current is dq over dt, the unit amount of charge crossing a given point per unit time dt. Now, how can we formulate this? Let's consider an area element on this ring, like so. So this area element will have charge dq, which is the dq in my formula right here. How can I express this dq? Well, the disk is uniformly charged with uniform surface charge density sigma. So by definition, dq is equal to sigma times dA, surface charge density times the area, the area element that we see in the picture. So I can rewrite this as sigma times dA divided by dt. The area element dA can be expressed in different ways. One way to express it is dx dy, for instance. That's a two-dimensional area element in Cartesian coordinates. But if you think about it, in this problem, we're going to integrate over rings, right? So it's best to use the area element formula in polar coordinates. In polar coordinates, the area element dA is equal to r d theta dr. If you're not sure why that is the case, feel free to check one of my other videos where I explain this. So substituting the polar coordinates area element here, we have sigma times r dr d theta divided by dt. Now here's something interesting. Take a look at this ratio. D theta over dt. Angular displacement per unit time. By definition, this is equal to omega, which is the angular speed. So let's rewrite di. Di is then equal to surface charge density sigma times angular speed omega times r dr. Now let's substitute this back into our integral. Here's our integral with di substituted. Now that we have our integration variable dr explicitly appearing in our integrand, we can also set the lower and upper bounds. R runs from 0 to capital R. In the next line, I'm going to pull out the constant terms so we can see the integral more clearly, and then we're going to do a variable substitution to actually take the integral. Now let's work on our variable substitution. I'm going to introduce this new variable u as r squared plus d squared. In that case, du will be equal to 2 times r times dr, 2r dr. That's du. And finally, we also need r squared. Rearranging this first line, we have r squared equals u minus d squared. Let's substitute these into our integral. I have used different colors so it's easier to follow the substitution. Also note that our integral limits have changed because we did a variable substitution. Now the integral runs from d squared to capital R squared plus d squared. In the next line, I'm going to separate out the integrand so we have it in two terms so we can take the integral easily. Let's integrate each term. The first term will bring a factor of 2 times u to the power 1 over 2. And then the next term has already a factor of d squared, but it also brings up a factor of negative 2, which makes this positive. So plus 2d squared u to the power negative 1 over 2 integrated from d squared to capital R squared plus d squared. Here's our final answer after substituting the lower and upper bounds and doing some simplifications.